Yes, I'll start recording before I start complaining about this software. So this is the Logitech high definition webcam. Oh wait, but I'm supposed to share screen, right? Somebody was saying that's what the note behind me on the board is for. Share application screen. But okay, so okay, somebody wants to tell me how to do this. It has a lot of lag. What? Yeah, no, this is, the problem is I have the webcam, but this is still, I can't, if I plug the webcam in, then Collaborate Ultra doesn't want to find the microphone. So then I can't speak. If I switch to the other window, you can see the video because the laptop can see the camera, but then Collaborate Ultra can't find the audio. So yeah, the problem is those are with the little camera I bought at Staples, which you can't buy a webcam at Staples anymore. They're all sold out. So I just went and got a normal camera. So it turns off every half hour, fine. But I can't hook it up to the computer for you to watch through it while I'm doing a lecture. So you can't see the video. Well, you can't read what I'm writing as I'm writing it. Oh, okay, close other apps. It looks like another app is using the camera already. So apparently I can't share the whole screen. Yeah, so now, okay, we've lost like 10, okay, not so bad, like 15 minutes. So now this is too far away because apparently, so somebody was asking me to share the screen to make it bigger. Okay, so what did they mean by that? Okay, so plug in the computer. Now I have to set up the little now I have to set up the camera and everything. Oh. Okay, so the camera is recording as well. So, okay, sorry about this. Okay, so I can, how do I switch it to speaker view? But I'm speaking, so why is it switch to current speaker mode? Okay, but I'm speaking. Can you hear me? So why isn't it, okay. So why is it not? So it's set on current speaker mode, but now it's supposed to, okay, stop sharing. So I'm sorry about this. So somebody suggested sharing the screen because it makes the image bigger. I'm sorry, I haven't had time to figure out how to do that with this thing because now it's set on speaker mode, but it's showing me one of you, even though I don't hear anybody else saying anything. You can hear me. I'm just going to go ahead and give the lecture and tell them afterwards that yes, I have the webcam now. I can't believe I cycled out. So Manju lives in Bedford, actually past Bedford. So I cycled out this morning to pick up the webcam because they're going to do the delivery tomorrow. And I wanted it for this lecture. And it's like 30 kilometers round trip. And I got home and I had like 10 minutes and I plugged it in and it doesn't work. So we could do this by Zoom because Zoom can apparently find the camera, but we can't do it by Collaborate Ultra. So I'm back to having the another little camera on a tripod sitting behind my laptop. And this I can't do either. But we're going to forget about the technology and I'm going to teach you algorithms because that works and is something I like. Okay, but it's a beautiful day. And it was actually, Bedford Highway is not the best ride in the world, but so just checking again, you can hear me. Okay, so I'm actually going to share my screen for a second. Not for, yeah, the entire screen. You have to, even though it's the entire screen, you have to click on it. So we're going to talk a bit more about knapsack because it's a classic problem. And last week we saw sort of three versions. We saw binary knapsack, which is you can take the thing, fractional knapsack, which is you can take the thing and you can cut it later. Okay, so you can, all the stuff you can cut to optimally fill your knapsack. And then we talked about binary knapsack, and then we talked about binary knapsack with uniform densities. And we saw that binary knapsack, we don't, is harder, the greedy algorithm doesn't work, it doesn't give you an optimal solution, but then we saw that it, for uniform densities, if you take the biggest thing first, you get at least a 2 approximation algorithm. And the thing, we don't actually have a polynomial time algorithm for knapsack. And it's strongly believed that it doesn't exist. So this cartoon is a bit misleading. So it's not the best cartoon. It's not the best drawn cartoon. But on the left, you have a list of appetizers. So it's supposed to be a snapshot of a menu. And then on the right, so it's above it says my hobby embedding NP-complete problems in restaurant orders. NP-complete, okay, so some of the notation is slightly, okay, just read hard for the moment. So on the right it says we'd like exactly 1505 worth of appetizers, please, and the server says exactly. Okay, here these papers on the knapsack problem might help you out, and it says listen, I have 6 other tables to get to as fast as possible. Of course, want something on traveling salesman, which is another NP-complete problem, and we may have mentioned it when we were talking about Hamiltonian path, right? So, this problem, let's consider this problem. So what you have is a bunch of numbers, and then you're asked if you can, so you have a bunch of appetizer prices, and you're asked, can you find a combination of these, and you can order multiple of the same thing in this particular case, such that the prices sum to exactly 1505. This is not fractional, okay? This is binary in the sense that if you order a side salad, you get a whole side salad. You can't say, I would like a quarter of a side salad, and I would like to pay only a quarter of the price of a side salad. Okay? I don't think I know many restaurants where you can do that. So, as you get from this cartoon, this is supposed to be difficult. Okay? It's like binary knapsack, binary knapsack in the sense that either you take something or you don't. So I've told you that we don't know how to do this in polynomial time. Now I'm going to show you an algorithm for it. But this is going to start off our new section of the course on dynamic programming. Okay? So I'm just going to write down. I could try to do this thing where I could share this window with you, and I could go back to the Collaborate Ultra, but I'm just going to write down the prices: 215, 275. 275, 335, 335, 355. 420 and 550. 420. Okay. Yeah, hide. Are you still there? Definitely 28 people? Okay. Still there? Why is it? I don't want to show my screen anymore. Why is it doing this? You're sharing an application. No, I'm not. Stop. Okay. So, is anyone there? 27, I just lost somebody. Okay, good. So you want 1505. So there's a problem. Oh no, let's not talk about that because the assignment is due tomorrow. So there's something on there about a greedy algorithm for making change. But I think I asked you for the algorithm, so let's not use that algorithm and see that it doesn't work here. So how would you do this? Okay. Well, let's consider some smaller numbers because the first thing you would do is divide by 5. Okay. But let's suppose that we had 4, 3, 12, and 5, and we wanted to know if it was possible to get exactly 22. Okay? So, with dynamic programming, one of the things you frequently do, essentially you always do, is you build an array. Okay? Does anyone know how to do this? I mean, quickly? Supposedly quickly. Okay. So, what I'm going to do is build an array. Let's say A. So this is going to be one-dimensional dynamic programming. So let's suppose that these are the costs of some appetizers. This is an expensive appetizer. And here, so this is A, and it goes from A0 to A22. And we want AI is true if we can choose appetizers to get total price exactly I. Okay? So, interaction. Can we choose appetizers to get price, total price, excuse me, total price exactly 0? Somebody. Yes, we can. So this is true. Okay, yes. Can we do it with price exactly 1? Yes, no. Price exactly 2. Price exactly 3. Okay. So we can see that because 3 is that price. But let's think about how to do this algorithmically before it starts. Okay, let's just keep going for a second. So this is 3. 4, yes. 5, 6. We're allowed to reuse them. Yes. Okay, so 6, we don't have an appetizer that costs 6, whatever, cents, dollars, units of exchange. But we do have something that we'll get that has price 3, and we can just take 2 of it. So what we can do is look back. Okay, so we can add 6, we can look back, well, we can look back 12. And this would be, is there something that gives us price minus 6? No. There are no appetizers for which G. Oh, okay. Oh, math. Maybe just keep aside, yes. Okay. Then we look back 5, but this is a no. So if we could get $1, then we could get 6 by taking whatever got us the $1 plus the appetizer that cost 5. So then we go back 4, and we get a no. But then finally we go back 3, and we get a yes. So, okay, so however we can get an order that costs $3, we can then add an appetizer that costs $3 on top of that, and it will then cost $6. Woo! So let's do 7. Oh, I'm going to run out of time. So, 7. We look back 12, minus 5, no. We look back 5, so 2, no. We look back 4, and we see a yes, which is 3. And also, we look back 3, and we see another yes. So actually, we can do this by either taking an order of 3, and then adding a 4 on it, or taking an order of 4 and then adding a 3 on it. So this is, what is 7? Is 7 a yes or a no? Anybody? Yes, good. I like being reassured that there's somebody still there. Okay. 8. Well, we look back 5, 12, no. We look back 5, yes. We look back 4, yes. We look back 3, yes. So this is definitely a yes. And then 8, 9, we look back 12, no. 5, yes. 4, yes. 3, yes. So basically, we can probably, we can actually keep doing this. So this, I just made up this example. So when we get to 22, it's probably a yeah. Yeah, because now that we have a row of yeses, at least 3 long, we can just keep adding 3. So it's definitely going to be a yes up here. So, so this is going to be so it's times 2 divided by 10. This is 106. This is 84. This is 71. This is 67. This is 55. And this is 43. So, and this would be times 30, 301. Okay, so that's just getting rid of one of the decimal places. Okay, so now if somebody gave you these numbers and said, okay, can you choose a subset of these that sums to exactly this? How would we do it? Well, we would say, okay, if we have a language that has Booleans, we would say bool, bool A, it's, well, okay, so this isn't actually, so it's 0 to 300 on 1. So normally you would, so you declare it with size 302. And then A0 equals true. And for I equals 1 to 301. Can you read this? Not really. Sure. Okay. So the only thing that the new webcam got me was wasting 20 minutes of class and like 2 hours making it to bed trip. So okay, bool A 0 to 301. Okay, better? Okay. And then you're going to say A0 equals true. Because you can order no advisors and they will charge you 0 unless they charge you cover and stuff like that. So then for I equals 1 to 301, this is going to clap. Do you all remember that AI is true if we can choose appetizers to get total price exactly I? Okay, that's how this is defined. So what we're going to do is, oops, I want another array, okay? So this, can you still read this up here? Int p equals 43, 55, 67. I hope I did this multiplication right. 71, 84, 106. Okay. So for j equals 0 to 1, 2, 3, 4, 5, 6, what do we do? Since you all like these curly braces. Random victim again. Logan Sutherland. Mohammed Ramazani, are you there? Logan Sutherland. Yes, okay, Mohammed. Do you have a microphone? P. Okay, it's because I just multiplied, I didn't want to deal with 3-digit numbers, so I just multiplied everything by, I just divided by 5. Well, actually, I multiplied by 2 and divided by 10, which is the same thing. So it's like 43 is because 21.5 divided by 5 is 43. Yes. Okay. I just like 2-digit number. This is still a 3-digit number, but it's slightly smaller. So this is, okay. Sorry. Yes. Okay. So yes, it's 580. Oh, right. Sorry. Probably messed things up. Okay. So, Mohammed, are you still there? Do you have a microphone? Could you turn your microphone on? Hello? I can't hear you. Do I have my volume on? Can anybody else hear? I can't. Wait. So one person can't hear. I can't hear anything. But somebody can hear. This is weird. I can hear. He's not on mic. Okay, you can hear me, but can you hear Mohammed? No. Mohammed, say something. Speak to us. Can somebody try their mic? Okay, but can somebody try their mic? Okay, but I can't hear anything. Devin is saying something, but I can't hear it. I get a spinning circle. Do I have to allow people to use wait, now I vaguely hear something. Maybe? Okay.
There we go.
Yes! Yay! Okay, so I'm sorry, but so you're the only one I can hear, so you have to tell us what to do next. Sorry. So A0 is true. We can or make an order of appetizers that has price exactly 0. Then for I from 1 to 301, we're going to do what we just did and look through all of these. So what do I write now?
Multiply j by the values of p.
Well, I'm just going to use this as an index. So, well, the first thing, okay, so Gabriel wrote it. The first thing, we're going to do what Gabriel just wrote. But first, we're going to check if I minus Pj, maybe I should make this bigger again. Can you read this? All right, so that's what you, if I minus Pj, first we're going to say it's greater than or equal to 0. And AI minus Pj equals true, then what? Yes. Okay. Then AI equals true. This online learning stuff is not fun. Okay. So we do this check so that we don't get a seg fault. Okay? Okay, yes, AI is true. Because if we don't do this, if we don't do that check, then we're looking before the array, and that's bad, and your computer will complain. If this is greater than or equal to 0, and this is true, then, sorry, I'm missing a bracket here. Then it means we can get, for some pj, we can get an order that makes exactly the price we want minus whatever this price is. We can get that, so we can get price I, right? So then for and then we say this closes the if, this closes the for, this closes the for, and then we print A30. So this will tell us, for question 4, no, question 4 on the assignment, I hadn't even taught you dynamic programming by the due date, by the original deadline. So that would be super mean. It would be funny from my perspective, but it would not be following the rules. No, what is question 4? No, it's in Canada a greedy algorithm works. Okay, so you can always find a minimum number of coins, and the question 4 is the coins one, right? Then you can do it with dynamic programming, but what I'm asking there is the greedy, in Canada, the greedy algorithm works, and in some incredibly stupid coinage systems, in some coinage systems, it doesn't give you the smallest number of coins. Yeah, it's not easy to find a coinage system that dumb, but they did exist, or they do exist, or at least they did exist. Okay, so can people see how this is working? Yes. So is this true or false? You coded it. Then how do you know? Ah, okay, so this is, so if we take 215 and you actually take 7 of those, I actually haven't looked for a solution. Then is it 7, that's 14, 7 times 15 is, yeah, okay, cool. Okay, so we set up the array. So A0 is true, okay? Because so we've defined AI is, it was here. AI is true if it's possible to order a selection of appetizers such that they have price exactly I, and it's false otherwise. So A0 is true because it is possible to order no appetizers and they have total price 0. A1 is false. A2 is false. In fact, everything up to A43 A42 is false. A43 is true. And then A44 is false. And then, but then we get up to A55. So A54 is false. A55 is true. And then it's false until A67, and then it's false to A71, and then it's false to A84, and then, which is true, and then it's true again at A86. So for each I, it's saying, well, I don't know if it's possible to, I haven't filled in this array cell yet, but if I knew all the array cells up to from A0 to AI minus 1, then how can I determine if it's possible to get an order that has cost exactly I? Well, it would, anything that has cost exactly I is going to be some smaller cost plus an item. So you can just go through all the costs of the items and check and say, okay, can I get I minus 43? If I can, then I say yes. In that case, I order whatever gets me I minus 43. And then I order another one of these things with cost 43. And then and then I say, okay, but if I can't get that, can I get something that has cost I minus 55? And if I can, then I order whatever gets me that price plus 55. So now I want you to code it, okay? This is only like 5 or 6 lines. So now this is optional, but take like, okay, we don't have a lot of time. Take like 4 minutes and code this, and somebody, okay, we're gonna have to go again when the first person is done. Okay. So it's just this, and then have it. I'm going to ask you. Yeah, once you've coded it, then I can ask you about different values here. Okay? Is this okay? Can you hear the street noise? Right. Okay, so we have, okay, it's not bad. I used to live in Santiago de Chile, and it was louder there. Okay. People usually don't honk their horns. So, are you coding it? This is, so, okay, we're behind, we lost 20 minutes, so I'm gonna have to keep going. But one of the things, this course has a reputation as being very theoretical, but I want you to, I mean, you get good at algorithm design by coding, by looking at the competition problems and not just thinking, yeah, I could do that, but actually thinking, yeah, I can do that, and I code it, and then you're sure you can do it. Because some of this stuff is not as easy as it sounds. So I think, I mean, there's, forget who said it, Knuth or someone. He said, like, if you've learned it, then maybe you understand it. If you can teach it, then it's something like, if you teach it, then you understand it better, but you really understand it when you've programmed it. That's not always true. So please code this at some point. Like, sure, you can put in different numbers, and you can see like what values can you get and what values can't you get. Okay, but code it to be sure that you can code it. Okay. So also the other thing is, you don't just want a true or false at the end. How would you change it such that you actually got an appetizer order? So, oh no, I forgot. So I set the camera so that it no longer turns itself off after 30 minutes. But now I can't tell when it's finished recording because it doesn't beep or anything. Because apparently the 30-minute limit on the recording is because the EU put taxes on video cameras, import taxes on video cameras, and they decided that it's a video camera if it can record for more than 30 minutes. So Canon put a limit on that it will only record for 30 minutes. You can apparently download Magic Lantern and get around that, but it voids the warranty. So okay, so we've missed like half an hour in high definition. So okay, how would you change this so that it didn't just print yes or no? It would print, if it printed true, it would be true or false. If it printed true, then it would also print an actual appetizer order. So how would we find out 7 times 43? So, okay, nobody's saying anything. So what you could do is say this is true, and then you have a little empty linked list. So true plus empty linked list. Or it doesn't have to be, I mean, it doesn't have to be a linked list. Just some sort of, it can be a string or whatever. So then you can say, okay, if this is true, so we decide that we can make an order with price I, by making an order with price I minus pj and then adding something of pj, then we can say, okay, AI is true plus, what am I going to put here? Well, abusing notation a bit, I'm going to put I minus pj's linked list with concatenated, which I'm going to draw as this symbol, plus j. Okay, so this, now if I see this is true, I can have it say, okay, if this is true, then if if A301, so if it's true, then print A301's list. Okay, do people see how that works? I have only 24 people, 23 possibly. If that 24 includes me. Okay, so you should be able to code it such that if I give you a particular number, then it will say yes or no. I mean, it actually only has to fill in the array once, but if I ask you, okay, can you get 292? Then it will say yes or no. And if I give you, and if it says yes, then you can print an array, an appetizer order that gives you that price. Okay, so I have about 20 minutes left, so I am not going to get through all the stuff I wanted to. So, what's weird about this? So you understand how this algorithm works. Let's look at how complicated it is. So if you're given some target number n, then you make an array of size 0 to n, so n plus 1. And then this loop, this for I from 1 to n, this executes n times. And then in here, this executes this inner loop for each execution of the outer loop. The inner loop executes as many times as there are prices. So, okay, this is going to take, say there are m prices. This is going to take, well, this is an array lookup, and then this is just an assignment. So this is going to take something like n times m, right? Oh wait, that's still the answer. So n times m. So this is order n m. Right? People like that? It's okay? So, but think back to that cartoon we saw at the beginning, right? Where it said embedding NP-complete problems in restaurant orders. NP-complete means it's hard. And I told you we don't have a polynomial time algorithm to answer knapsack. This cartoon was saying this is something like knapsack. Well, but here we have this is quadratic, right? So this is a little bit subtle. Okay. So on the one hand, we start out, I tell you it's hard, and then on the other hand, we just came up with a solution for it. And I wanted to make you code it, but we just kept going because we're running out of time. So what's the answer? I mean, is this a special case of that problem? And the answer is not really. But this, when we talk about hard problems and polynomial time, we mean polynomial time in the size of the input. So how big is this input, these numbers? Well, you'd say, well, it's like, what's the sense of the size of this? And you'd say, well, the size is like 301. And in order to teach you why that's wrong, I'm going to give you I'm going to sidetrack a little bit and talk about factoring. Okay, so people know this. Okay, good. I'm going to erase it. So factoring means given a number n, give me a list of its prime factors. Okay. So this is the basis, the difficulty of factoring. Maybe some of you have heard that factoring, it's not known to be NP complete. But is believed that we don't have well, it's believed it's hard. Some people believe it's hard, some people don't. But we don't currently have a polynomial time algorithm. Okay. So if any of you have seen, there's a movie Sneakers with Robert Redford, River Phoenix, James Earl Jones, Ben Kingsley, Dan Aykroyd, and some other people from years ago. And it's about what would happen if somebody figured out a polynomial, a fast algorithm for factoring. Okay, and people are murdered, and the mathematician who finds it is killed, and all this kind of stuff. So now I made Alan find Huffman's algorithm. Now I'm going to make some poor person tell me an algorithm for factoring. Okay, so you can, this isn't really dynamic. This isn't dynamic. This is easy. So does somebody want to tell me how, if I give you a number n, I want you to tell me all of its prime factors. In fact, no, forget prime factor. I want to know all of its factors. Okay? And I want you to do that in time O of n. Is there anybody still there? I've lost even more people. Okay, so to keep things, to try to get back on track, now I'm going to choose somebody. Yes, so it would be for I equals 1 to n, if n, let's not do that, let's put mod I is 0, print I. And if n4. So print statement, consider a constant time, modulus, consider a constant time. So this executes once per execution of the loop, and the loop executes n times. Yeah. But you don't have to. I mean, yeah. So what Liam's suggesting is basically the sieve of Aristophanes, but But in this case, I just said O of n time. This will do it. Okay. So what's it? I mean, they made movies about, you know, spies killing each other to try to get a fast algorithm for factoring. And here, Gabriel and Riz, Liam are saying, yeah, we can do it quickly. Okay, so what gives? What's the weirdness here? And the weirdness is here we're talking about a number n. Okay. But what is the size of your input? Well, it's not really n, okay? Because if I write the number 7143279, okay? How big is what's actually being passed to the program? Well, it's a number, it's 1, 2, 3, 4, 5, 6, 7 digits. Okay. So now, if I add another 7 digits, 8, 2, 3, 4, 6, 1, 5. So the size of this input measured as looked at as a string has only doubled. But this number got a lot bigger. Okay? So basically, if you double the number of digits, you sort of square the number. Square the maximum value of the number. So you go from being bounded by 10 to the 7 to being bounded by 10 to the 14. Okay, so if you look at if you're measuring the input as sort of this as the number, then yes, we can do this in polynomial time. But if you look at it as the size of the number, then we don't have a polynomial time algorithm for it. So basically, what people want when they say we want a polynomial time algorithm for factoring, what they mean is we want something polynomial in the size of the logarithm of the number. And that we don't have. So the same thing, when we did this array from 0 to 301, that's taking, that size of that array is linear in the number, in the target number, but it's not, but that is exponential in the number of digits in the number. Okay? So this is tricky. Now there are some problems. So for example, if we took factoring and we didn't express the input number in decimal or in binary, if we expressed it in unary, so in unary, the number 7 is just 1, 1, 1, 1, 1, 1, 1. That's 7 in unary. So then, in unary, the size of the representation of a number is the same as the size is the same as the number. So if the input to your program, to your factoring program, if the input is expressed in unary, then yes, it will run in basically linear time, as long as you sort of convert and then actually do the math in binary. Okay, sneakers is not. I like it, but for example, you've probably heard of quantum computing. One of the reasons why people have been hunting for quantum computers, maybe not the main reason anymore, but one of the reasons it sort of quantum computing sort of got started a long time ago was that a guy called Peter Shor found an algorithm, polynomial in the size of the logarithm of the number, for factoring integers on a quantum computer. Okay, so Shor's algorithm is still, if you ask, well, what could you do with a quantum computer? Now people say we can simulate quantum systems and stuff like that. But it used to be that if you say, what can you do on a quantum computer that you can't do on a classical computer? People would say, well, you can factor by Shor's algorithm. So there are problems where even if you express the input in unary, it remains hard. Okay, we still don't have a polynomial time algorithm for it. For example, if you think of three coloring, if you express all of the numbers in unary, well, each vertex, you could write all the adjacency lists by writing each edge is represented as a number. So you've got the vertices from, say, 1 to n, and then you've got numbers from 1 to n. So if you now write these numbers in unary, well, you expand by n, but your input was already of size at least n. So you're at most squaring the size of the input. If you square the size of the input, then the running time of your algorithm is allowed to be like, if it's bounded by a polynomial in the square, then it's still bounded by a polynomial in the size of the original input. Okay, so this is why we have this inconsistency. Why you read that cartoon and you think, yeah, but didn't Travis teach us an algorithm for knapsack? So you can modify that algorithm so you have to use a two-dimensional array. You can modify the algorithm such that it only uses one of each appetizer, and this is more in line with the original knapsack problem, because then you have an item and then you can take it or you can leave it. But just because you take it, it doesn't mean you can take another one. Maybe you don't have an infinite supply of each item. Okay, now this is where I sort of, okay, this is going to be scribe mills for one group. I want to give you another example of something you can do with dynamic programming. And that's maximum sum subarray. So people are leaving, but this is interesting. The interesting part, uninteresting part. Okay, so I have to do this in like 6 minutes. You can do max sum subarray with dynamic programming because what do you do? Well, suppose you have the input array, which is called, what was it called? Nums. Yeah, let's say it's called nums. And it was from 0 to num size minus 1. Okay, so now, to do this with dynamic programming, what we're going to do is say we're going to have an array A, which is also going to go from 0 to num size minus 1. And I want it such that AI is the sum of the max subarray and I want this max subarray of length greater than or equal to 1, okay? That ends at, so this is max subarray in nums, at nums I. Okay. I'm giving this whole lecture to like 20-something people out of a class of 111. Okay, but at least it's recording through my crappy webcam. Okay, so this means if there's a maximum sum array, it ends somewhere. So if we can fill this in from A0 to A num size minus 1, then we can just skim over this and look what the maximum number is and say, okay, that's the maximum sum of any subarray that ends anywhere. So we return that number. Okay? So how does this work? Well, AI, suppose we filled in from AI, from A0 to AI minus 1. We filled all of those in, and now we want to fill in AI. Sorry if this is hard to read. So what can we do? Well, we have to take AI, okay? So what are the two cases? And I'm running out of time. Okay, before we get to 1255, I'm going to tell you, I'd like you to actually code this. And then, as a dynamic program, and then I want you to write on LeetCode to solve the max sum subarray problem, okay? And then, once you've got that working, it worked in linear time. So remember, our divide and conquer algorithm was n log n. And when we were talking about reductions, I said that, look, you can reduce max sum subarray to max sum circular subarray in linear time and backward and vice versa. So that means if somebody gives you a linear time solution to max sum subarray, you automatically get a linear time solution to max sum subarray in a circular array, also in linear time. Why? Because if somebody gives you an instance of max sum subarray in a circular array, you take it, turn it into two instances of max sum subarray, solve each of those in linear time. You turn it into two instances in linear time, solve them in linear time. They don't get bigger. Okay, you solve them in linear time, and that gives you the answer for your max sum subarray in a circular array. Okay, yay reductions. So once you've figured out, I wouldn't tell you, but it's not hard, and I have 1 minute left. How you get AI? Well, okay, I don't have time to write. You look at AI minus 1. If this is positive, then you can get more by taking whatever ended here and this. But if this is 0 or negative, then you just take this. Okay? So it's AI. If AI minus 1 is positive, then AI is AI minus 1 plus nums I. And otherwise, if AI minus 1 is 0 and negative, then AI is just nums I plus nothing. Okay, implement that, get it going on LeetCode, and then use that solution to solve that other problem on LeetCode, max sum subarray in a circular array, because that way, just take your code, do not change it, just take it and paste it in as a subroutine, and then call it twice, right? Because that way you get practice on dynamic programming, and you get practice seeing on reductions, which is going to help you when we get to NP completeness. And I'm out of time. So again, I'm sorry that we lost a lot of time fighting with technology, and I will try to have the new webcam working for Wednesday. Possibly I will end up running this through Zoom or something. Questions? People are just leaving. Oh, okay, good. Everyone understands. I'm sorry, really, I would have tried it, but I literally got back right before the class. Okay, so when you say does it need to be done? You're given this as the input. So you're given, remember, it's like something like you're given something like void max subarray, and this takes int pointer nums and int num size and returns. And now you do this, whatever, and then you print or return. Yes, but then you're overwriting your input, which is a side effect. Oh, so yeah, if you want to actually return this, then you can do the same trick where if this, in addition to the number, it's also storing a list of the values. Well, actually, you don't need a list of the values because it's a continuous range. So if it stores the starting point, so if it stores the starting point of the max subarray that ends here, maximum subarray that ends here, if this is positive, this takes its starting point, and if this is 0 or negative, this says its starting point is I. If you want to return the contents of the max subarray, then yes, you better keep this lying around. But in general, it's unless somebody has told you, you actually get to use the space for the nums array, because remember, it's being passed as a pointer, which means you've all seen this call by name and call by value. Yeah, so if this is being passed as a pointer, that means whoever, they're not making a copy of the array and giving you the copy, they're actually giving you a pointer to the original array. And so in general, it's dangerous if somebody is giving you a pointer to an array and asks you to compute a function on that, it's then playing with the array is a side effect. And if they're not expecting that, it can be bad. So, like, if people ever make you learn this, functional programming is predicated on side effects being terrible. Maybe. So I could. So okay, yeah, please code up the maximum subarray. If you really want to understand that appetizer problem, code it. Okay? Get it so that it's actually telling you 7 times 43 or any other solution. You can play with it and have it count the number of possible solutions. Okay? How would you do that? Well, you would look at all of the PJs, and you say for every PJ such that you get a truth, then you have an option. Now that's if the order in which you order the appetizers matters. Okay, just play with this stuff. Post up and get it going on LeetCode, and then because eventually, I mean, while don't agree that if you can code it, you really understand it. But the opposite is, it's not true that if you can code it, you necessarily understand it. But it is true that if you can't code it, then you don't really understand it. I don't code a lot. I get other people's grad students to do that for me. But in a pinch, I can code. Now, I code in NCC because it doesn't have any, I don't like technology. And in NCC, it's, this nice standardized, and I can learn that, and it doesn't decide that this tool is not going to talk to your webcam now, but this other tool will, and all that kind of stuff, and it doesn't turn itself off. I'm sorry about my bike only has one gear, so which is great for maintenance because I don't like technology, so I don't like messing around with fixing gears. But my Bedford and back before the class, I'm really disappointed that that webcam doesn't just work. It will probably work. I'll plug it in and get it going this afternoon maybe, but I didn't have time. I'm sorry. But we have a webcam. And actually I ordered a webcam myself, and maybe that will arrive and maybe that will work. Good luck with the assignment. And yeah, welcome to dynamic programming. Now I will go and have breakfast. I was only eating that apple because I was really starving. Okay, cheers. Stop recording.